Okay, welcome to diffraction, and then we'll be discussing single slit diffraction in particular. So we have, let's a little review. Diffraction is the spreading of a waves, whether it goes around an obstacle or through an opening. Now in this particular picture here that you see, this is no diffraction because you can see that the waves are pretty much going linearly outwards. And pretty much here, this is also no diffraction. However, as this opening here, which we're going to be calling A, gets quite small, approximately equal to the wavelength or less than the wavelength, then you get the diffraction and you can see the waves are starting to spread. And so this spreading of the wave is called diffraction. This is diffraction with water waves. We also can observe it with sound waves. If you look at it with light, you can also get it as well. So these are light waves. These are the wave fronts. The light is coming this way, and here is the wave spreading in all the different directions, and you're getting diffraction. So you can get that with a small aperture, or you can get that with a slit. Now there's a main theory that we should probably review called Huygens Principle, which is listed down below. Christian Huygens, a Dutch physicist, came up with this theory, and he said that every point along a wavefront can be considered as a new source of producing its own wavelets. So essentially, every part of a wave is an infinite source of new wavelets that spread outwards and produce their own waves. So if you have a slit with opening A, then all along through that opening there are many points. We've just drawn 3, and these 3 points here are interfering with each other and producing an interference pattern on the screen. So now let's discuss the diffraction of a single slit. And so in this picture on the left side, this is not diffraction because the opening size is quite large, and so you're just getting one bright line and you don't get any spreading occurring. However, if A becomes quite small compared to the wavelength of light, or close, actually at least approximately equal to it or less, then you'll get this diffraction. So you get this big bright central fringe here, and you'll see that you'll get some dark bands here and here, and further ones that get outwards. So the pattern looks like this if you were to use a laser. If you're using a monochromatic coherent source, like a red laser, then you would get this bright band right in the middle, and then it would drop off here, destructive interference. You can see here m equals 1, m equals 1, and then another bright band here. And what we're really looking at is to see how wide this bright band is. And so typically then we're looking really for the destructive interference that are occurring here and here so that we can find the angular width or the distance x of this bright band. Okay, and this pattern that you're seeing here is called an interference pattern, this is sometimes asked where you have to plot the interference pattern, just the general shape of it. Now let's take a closer look at the mathematics on the next page. So here I've drawn a little bit of a diagram to show here is our single slit. This distance here is going to be labeled as A, and here are our waves coming along here, and now these little points that I've drawn here, I just drawn 2, are basically little wavelets that are creating their own new waves, and these are moving off, diffracting, and creating interference pattern over here. So we can consider many infinite amounts, but what we're going to do to simplify this is we're just going to look at one point that's at the very top and one point that's in the middle here. So we're going to consider 2 rays, one at the very top of the slit edge here, and then one coming from the middle source. Now there's an infinite amount, but we're just going to simplify this and take one from the middle and one for the very top. So the distance between these two things are basically off by half of the width A. So if I draw in a triangle in here like this, and this little distance here represents the path difference, similar to what we had when we did double slit interference. And we can call this little angle in here theta. And so once again, if we want to get destructive interference, then we want these two rays that say this is ray 1 and this is ray 2. Ray 2 will travel a little bit extra distance, delta r or delta L, and that extra path difference we want to be a multiple of a half wavelength. And using this triangle, we can see that sine theta is delta r divided by a over 2. So the path difference is a over 2 times sine theta. So you can see where that comes from, and then half of a wavelength, or 1.5, or 2.5, or 3.5, and so forth. So I'm just doing, say, for the first one, and then we can change that. And what you'll see is these 2's cancel out. And so you get this formula right here, that a sine theta equals plus or minus lambda. And if we want to get the second or third or fourth, we would just put in an m in front. And so this formula is the formula for destructive interference. So you notice that this is the same formula that we use in double slit interference, except this was the formula that we used for constructive interference. So notice and be careful that this is the same form as the two slit pattern, but this gives you it for dark fringes. Okay, so try not to mix them up. Okay, and note that m equals 0 is not shown in here because m equals 0 you don't have that order. Okay, the first order is going to be really the bright spot in the center. So there's your interference pattern. What we're solving for is this distance here. And I've labeled this as y. We can probably call this as x instead. So if it's consistent with the AP notation, and so you can call this delta x. And this is x sub m for the mth order. So this is very, very, very much the same as what you had in the AP formula for double slit interference, except this is now for single slit interference. Okay, so I think we're now ready to tackle a problem. So take a look at the next page, example number 7. In this problem, we're given a helium neon laser with a wavelength of 633 nanometers. So that's 633 times 10 to the power negative 9 meters. And it is a distance of 6 meters. Now they use an R in here, but AP notation would be an L normally on the formula sheet. So this is 6 meters here. And then we're asked, we said, you find the distance between the centers of the first minima, right here to here, is 27 millimeters. So 27 millimeters is representing the distance y1 or x sub 1. But that is actually 2x, because remember this is x sub 1 going up or down, so really twice that is 27 millimeters. So x sub 1 would be 27 millimeters divided by 2. So that's 13.5 millimeters, or 13.5 times 10 to the power negative 3 meters. And we're asked to figure out what is the width of this slit A. So what does A equal to? Now we're going to make an assumption here. We're going to assume that theta is small. And that way we can use the small angle approximation and go straight to our formula that x sub m equals m lambda L all over d, but it's actually A in this case, for destructive interference. And we're going to be solving for A, so let's rewrite that expression as A equals m lambda L all over x sub m, where we're looking at the first order fringe, so m is equal to 1. So A equals 1 times 633 times 10 to the power negative 9 meters. L is 6 meters. And x sub 1 is 13.5 times 10 to the power negative 3 meters. And you'll get an answer of 2.81 times 10 to the power negative 4 meters, which is equal to 0.2 8 millimeters. And so that is the angular width, not the angular width, the width of that slit opening. And just a small little reflection to note that I didn't mention earlier is that if I were to ask you to find, say, x sub 2, hopefully you don't have to go through all this calculation, because you would just simply be placing a 2 in here for m, but really x sub 2 would just be twice x sub 1. Just like if you were to find the third dark spot, that would be basically 3 times x sub 1. Okay, and that's it for example number 7.